Jose Senovilla. And I think those who have been aware of the activities over the last year or two regarding singularity theorems, they would know Professor Jose's name very well. Even his name has been cited in a Nobel Prize last year, when Roger Penrose got the Nobel Prize. And the reason is very good. Jose had made many important contributions, improving the singularity theorems, clarifying singularity theorems, taking it even beyond classical general relativity. So we hope that today he will enlighten us a little bit about the singularity theorems in gravitation. And with this, I would request Professor Senovilla to please, the floor is all yours.
Okay, so thank you very much for the kind introduction and for the invitation. I'm going to talk about this singularity theorems in gravitation. This gravitation is taken in general, so this is not only in GR. And this is the outline of my talk. So I will start with a brief introduction, then I will devote some time to the important Penrose singularity theorem. And then after some review of other singularity theorems, I will pass to give you some examples and some relevant remarks about, some folklore and ideas that people have about singularity theorems, which are not completely correct. Of course, we all know that the singularity theorem by Penrose won the half of the Nobel Prize in 2020. This is a very a well-deserved award, because the theorem, apart from its mathematical beauty, contained novel ingredients and many ideas which happen to be very fruitful in gravitation. This theorem prompted multiple developments in relativity and also had some physical consequences, like, for example, whether the theory is incomplete or we have to look for something else, etc. And a very key point is the notion of trapped surfaces or trapped spheres that were introduced in that paper by Penrose, and this is a fundamental idea today in gravitation. It's the key idea in black hole physics, in numerical relativity, in mathematical relativity, even in cosmology and analogs, etc., etc. This was really a very, very clever idea that completely changed the path of relativity. And its influence is still going on today. Now, as I proposed some time ago, and actually this was cited by the Nobel Committee, in my opinion, the singularity theorems constitute the first content of relativity which is truly post-Einstein, in the sense that everything that happened before, and you name it, whatever, the ADM formulation, the deflection of light, or whatever, and also many of the things that came next, like background radiation or gravitational lenses, etc., all of this was somehow foreseen or predicted or suspected by Einstein. But I believe that the singularity theorems and their consequences were not even suspected by Einstein. So in this sense, no. Sorry. So in 1965, general relativity became a new theory, which was completely mature physical theory with many surprises. So let me pass to the Penrose singularity theorem. It looks like this. It has three assumptions: the null convergence condition, the existence of a non-compact Cauchy hypersurface sigma, and the key idea, a closed future trapped surface. And the conclusion of the theorem is that there are null geodesics which are incomplete to the future. Now, you may notice that there are some colors here. This is because I will keep these colors for the different assumptions in the theorem. I am not going to talk much about the Cauchy hypersurface. This is a basic idea in gravitation, so I hope everyone understands. This is essentially an instant of time which is good enough to predict the entire future and also the past of Euro space-time. Now, there were two important novelties in this theorem and two fundamental ideas. One is the characterization of singularities by geodesic incompleteness. And the other one is the concept of the capped surface. So I'm going to talk a little bit. I'm going to start with the convergence condition. The convergence condition was based on an idea by Rai-Chaudhuri, who is this important person here. And the Rai-Chaudhuri equation, which was found in 1953, but only published in 1955, is this identity. This is actually an identity in Lorentzian geometry. Here, V is a vector field that I'm going to assume causal, so either time-like or null. And nabla is just the covariant derivative. This is the Ricci tensor. Now, this identity, if the vector field V happens to be tangent to some geodesics, then of course, if the integral curves of V are geodesics, then this term here vanishes. This is what I am writing here. If you also assume that these geodesics emanate from a point, or if they are orthogonal to surfaces or hypersurfaces, depending whether they are null or time-like, then you can assume that this is symmetric. And then this equation collapses to this very simple form, where on the left-hand side you have the derivative of the expansion of the pencil of geodesics along the geodesics themselves. And on the right-hand side, you have something that has a sign. It has a sign, because this thing now is positive. You can prove that. And this you may ask to be positive on some grounds that I will explain now. And then what you get is something that telling you that this is negative, and then it's very easy to prove using elementary mathematics that if the divergence or the expansion is negative at a point, then it will become infinite in finite time, or if you want infinite affine parameter. Now, these are not singularities. These are caustics or focal points. So these are places where the geodesics tend to cross each other and things like that. The important idea behind this for the singularity theorems is that geodesics which have focal points or conjugate points, these caustics, then they stop being maximizing between 2 points, because you know geodesics maximize the interval all the time. Now this is called the focusing effect, and one needs a geometric condition because we need that this has this sign. And this is usually called the convergence condition. If it's called null convergence condition if V is for a null vector, and time-like if V is assumed to be time-like. And now they are usually called energy conditions. Why? The question is that in general relativity, you can't relate the Ricci tensor to the energy momentum tensor via the Einstein field equations, which are these ones here. And of course, then you can rewrite this as a property of the matter, of the energy momentum tensor. And this is why the convergence condition sometimes rewritten in terms of physical quantities is called sometimes the strong energy condition. I want to insist, this is the geometric condition, and you can use it in your favorite theory, whatever it is. Only thing is that maybe it has no support from energy contents or things like that. Now, the first key idea was this of proving incompleteness. You see, in general relativity, it's very difficult to define what is a singularity, because singularities, if we think that these are places where the curvature blows up or things like that, they are not part of the space-time. And also, there may be singularities, and you may not recognize them from the Riemann tensor or the curvature tensor, because maybe all the curvature scalars, the scalars vanish. This happens, for example, in plane waves. Still, the space-time could be singular. Now, the idea by Penrose is that space-time fails somehow at singularities. And therefore, these places are not part of the space-time. Now, his idea was to use physical curves that actually do belong to the space-time to point towards the singularity. because curves with I don't know, going to the future or to the past are good pointers. So if these curves cannot be continued, and then they are pointing towards a problem. When I say that they cannot be continued, I mean that it has elapsed, say, a finite time, but then you cannot go further. In that case, then we say that there is a singularity, because these are pointing to a problem. Now, the idea of a singularity does not need that the curves are geodesic. And as a matter of fact, there are known examples where you have a geodesically complete space-time, but there are curves with bounded acceleration which are incomplete. Nonetheless, all the singularity theorems so far in history merely prove the existence of incompleteness, of geodesic incompleteness. Of course, this is sufficient. This is more than enough to prove that the space-time itself is incomplete. This was the first key idea by Penrose, and the other key idea was the concept of a tapped surface. Now, let me explain this with a picture. Now I'm taking here a space-time. T goes up as usual, and I am removing one dimension, of course. Then I take one of these instants of time, t equals t naught, and I draw the circle. This circle is like a sphere in the actually four-dimensional space-time. And from this sphere, I let things to travel out and in. And of course, we all know that light is the thing that travels faster. So after the dt of time, infinitesimal time, things can go out up to the blue line, for example, and in up to the red line. So you can think of this as the places where the light has been able to travel. Now, this is what I call a normal situation, and this is very intuitive. So light going outwards or light going inwards will form a new, bigger or smaller circle. And now what happens if I am in a dynamical situation, like, for example, what happens in the universe, which is expanding, or in the collapse of a star? Now, in these dynamical situations, it may well happen, that the space is what is the opposite of contracting? It's contracting, the space itself. So this is what I represent here by drawing this instant of time smaller than the original one, because it's the space which is contracting itself. Now, in this case, everything works as before. The blue line will be outside the yellow line and the red one inside. But you have to compare the blue line with the original yellow line at the original time. And it may happen in these dynamical situations that the area in this picture, it will be the length of the blue line is smaller than the area of the original surface at the original time. And this is, if this happens, then we say that this is a cupped sphere. Now, this is the picture. Now, let me just show you a little geometry. Now, this idea of tapping can be extended to any submanifold in your space-time. It doesn't have to be a surface. This is something we realize much later, only in this century. But if you take a space like submanifold in space-time, any dimension, and then you call, so this is the name of the submanifold. This is going to represent whatever it is, the area if it is two-dimensional, the volume if it is three-dimensional, etc., the length, whatever. Now, what you do is geometrically you take this submanifold and you deform the submanifold along a vector field. So the vector field here is called psi. You take the integral curves of this vector field, you follow them a little bit, and then you have deformed the original submanifold. And then it's a very simple calculation to check what is the initial variation of area or volume or whatever it is. And the initial variation of the area is this integral on the original surface or submanifold. Here, this is the tangent part of your deformation vector field. And this is the scalar product of the deformation vector field with H, which is the mean curvature vector. The mean curvature vector is the trace of the second fundamental form of the submanifold. This is a vector field on the surface, which is orthogonal to the surface, which is geometrically very well characterized. Now, if two submanifold is compact, then this disappears because the integral of the divergence is 0. So if you have something which is compact without boundary, like a sphere, this disappears, and then the variation of area is just the scalar product of the mean curvature vector with your deformation vector. By the way, this is just a classical result in Riemannian geometry. This is the one that characterizes minimal surfaces in Riemannian geometry. They are given by a vanishing mean curvature vector. And in pure Riemannian geometry, with the positive definite metric, there is nothing else which is distinguished. So either H is 0 or not. And if H is 0, they are called minimal surfaces because the area is on a minimum. What happens in Lorentzian geometry? Well, in Lorentzian geometry, your mean curvature vector can be time-like, for example. Then what happens if your mean curvature vector is future time-like in your original submanifold? Well, then if H is time-like and then you make deformations to the future, then this product is negative because it's the product of two time-like vectors pointing to the future. So the area decreases no matter how you choose your deformation vector to the future. You see, and then this is the main idea behind trapped surfaces. This is the geometrical definition of a trapped submanifold. If you have the mean curvature vector, which is future time-like, then this is trapped to the future. And of course, you can do the same to the past if H is path pointing and time-like. By the way, there is a marginal limit which happens when the mean curvature vector is future light-like, and then these are called the marginally future trapped surfaces. These are, for example, ones that you see at the horizon in the black holes like Schwarzschild or others. Now, if you are following me, you will observe that in stationary spacetimes, compact trapped submanifolds cannot exist. So you need something which is dynamic. It's very easy to see because if you are in stationary spacetime, a Killing vector is time-like, and then along Killing vectors there is no variation of area, of course, and therefore this scalar product can never be negative for the time-like Killing vector. Now, if you have the mean curvature vector and then you take the scalar product with any normal to the submanifold, then what you get is a scalar that is called the expansion along this normal. So you see, for a future trapped surface, all the future expansions, so all the ones that you can construct with normals which are to the future are negative. And this was actually the original definition by Penrose, that the two null expansions to the future are negative. Now, what is the relevance? So I started with the geometry and I come back to things having to do with physics. Now, what is the relevance of this concept and the Singularity theorem, for example, for cosmology or for gravitational collapse? Well, Hawking quickly understood immediately that such trapped spheres do exist in Robertson-Walker geometries. And then he and Bob Gerock proved several singularity theorems that have cosmological applications. So let me consider the case of the Friedman-Lemaitre Robertson-Walker metric. So this is the standard form of the flat. So for simplicity, I am using that the space is flat. So this is just the Robertson-Walker flat metric. Now you can take the round spheres given by p equals constant and k equals constant. So these are round spheres, and then you can compute the mean curvature vector for this. If you compute that, this is what you get. You have to believe me. Here, a dot is the derivative with respect to time. Now, you may then ask, when is this main curvature vector time like? Well, this is just a trivial calculation with the metric, and this is time like if a dot square is greater than 1 over chi square. So you see, if you take chi large enough, and you can take chi very large because this goes to infinity, then this is always going to get less than whatever is a dot. So as long as a dot is non-zero, for example, if your universe is expanding or contracting, then you will always have round spheres. Now, if you consider this condition now, meaning now at instant of at this time in the universe, then you can rewrite this as a condition on the Hubble parameter, and d, where d is the proper distance to the sphere that we want to know if it's found. So as long as the distance is large enough such that this holds compared to the Hubble constant, then these are the spheres in the universe. In this case, they are past trapped because the universe is expanding. Now, so this is the relevance for cosmology, and I will tell you a little bit later why, because this is not only for Robertson-Walker, it will be for other cases. Now, what is the relevance of this concept for gravitational collapse? And now what we have here is this iconic picture that you can find in Penrose's original paper, not this one, this is the one devised by the Nobel Committee, but is essentially the same as the one by Penrose. Now, this is supposed to describe a collapsing star, so this is the matter, collapsing in the sense, so time goes to in the vertical direction, up, the matter collapses, and then it forms something which we are going to call a black hole. And then there is something called the event horizon and things like that. And in the original picture, the idea is that the light cones, so light cone at every point, we all know that light is affected by gravity because of deflection of light or gravitational lensing. Now, you can describe this by, tipping the light cones when you have in very, very strong gravitational fields. And this is the idea here. So you tip the light cones, and they can tip so much that in the end, you have to go towards the center between quotes, because this is not going to be the center anymore. I will explain in a minute. And also, this is inevitable because you have to go to the future, you see. So this color in the light cones means that this is the future where you can travel. Okay, and then you see that there is here this circle that is supposed to be a capture. Now let me explain this in another way, also devised by Penrose. And let me first start with the basics. So what is what we are going to call a horizon? And of course, horizons already arise in special relativity. So in special relativity, if you take a particle which is accelerating, in this case with constant acceleration, say in the x direction, then this is the trajectory. So O here is the proper time. So we don't move in the y and z directions, only on x. Here c is the speed of light, and a is the constant acceleration. You can check that because if you compute from here by taking the derivatives with respect to proper time, you get the for velocity, which looks like that, and the for acceleration, which looks like this. And you can easily check that the velocity is properly normalized, that the acceleration is orthogonal to the velocity vector, and also that the norm of the acceleration is a squared. This is why we say that this constant is the constant acceleration. Now, another way of looking at this trajectory is that this describes a hyperbola in the plane CTX. This is what I'm going to draw. So I take now CT and X, and the hyperbola that describes a constant accelerating particle is this red line, P is the particle. So I took by convenience this original starting point at the original t equals 0 time. Now, you may see that this hyperbola has a asymptote, which is this line here. And of course, if you remember that we are using CT here, light cones are at 45 degrees. So for example, the light cone for this point is these lines. It can affect anything which is within this green lines to the future. And in particular, this point here can affect your particle at this instant or later. But what about this other guy here, X2? This X2 will never be able to influence in any way or to communicate with the particle at all. So this is why we call this the horizon. From the other point of view, this particle here, which is accelerating, will never be able to see or to receive any influence or to feel anything which is beyond or to the upper side of the horizon. And this is why this is called the horizon for this particle. Well, this is probably well known for by many of you, but now let me go back to the picture. Now, the idea by Penrose was, let's take this picture and then let's put the light cones at 45 degrees by definition. So instead of letting the light cones keep, what you now force is all the light cones are going to be at 45 degrees. So these two little lines here or there mean this is the light cone, and the arrows point to the future. So this is supposed to represent, again, the collapse of a star. Now, to create a better idea of this picture, what I recommend is that you create yourselves an image in your brain by taking the revolution of the picture along the star center. Okay, so around this, you take the revolution, and then what you will get is like a cylinder of red, and then your universe with one less dimension. Now, given that we have forced the light cones to be at 45 degrees, now if you take any r equals constant line, they will look like this, you see, and they look like hyperbolas in the previous one. But only up to the horizon, which is given by the gravitational radius. Here, m is the total mass of your star. Gravitational radius sometimes is called Schwarzschild radius. So if you take different values of r equals constant, you will get these lines, which are time-like everywhere. This line, which is null, and the other ones, which are beyond the horizon, which happen to be space-like. And eventually, r will get to 0, and this is the singularity. So this singularity here corresponds to this line there, which is the singularity. Now, what about the trapped surface? Here, you look at this like in the circle. In here, this would be this. Of course, if you take your imaginary picture of this, it will go like around. So this will be also a circle. But you see, it doesn't matter how you go to the future. It doesn't matter how you go to the future, which are these two lines. You will get to smaller radius between quotes, because now r is time. So you will get spheres which have smaller area. So it doesn't matter how you go to the future, the area decreases, and decreases until it goes to area equals to 0. Now, you may see that the horizon distinguishes between the particles we live outside the black hole, so those which go to infinity, from those which will never go to infinity. For example, if you let yourself follow into the star which is collapsing, you may follow this line and end up in a singularity. Okay. Now, by the way, this is usually drawn in a different manner, which is called a Penrose diagram. So you take this thing, but then you compactify this so that you bring the infinity to finite values. So these lines here are actually infinity. And then all the lines outside will eventually go to this point, which is called I plus. But this is just to show you the very same idea, keeping 45 degrees for the light cone, but compactify. These are called Penrose diagrams. Now, let me go to the important point about trapped surfaces. The important point is not the definition. The important point is that they are stable. Because the notion of Katsu manifold is, first of all, is independent of whether you choose bases or coordinates or anything. And of course, they are also independent of the existence of symmetries. mean spherical symmetry or things like that. But the decisive point is that the definition, in the sense that the mean curvature vector has to be time-like or the expansion is negative, is given by inequalities, and therefore they are stable. If you perturb your thing, it will remain with this same property. Now, a very fundamental thing of GR is that the Einstein overfield equations, for example, describing a perfect fluid, are hyperbolic. And this also happens for the chromatic field or the scalar field, etc. This means, from a mathematical point of view, that they possess the property of continuous dependence on the initial conditions. Now, the initial conditions on the Oppenheimer-Snyder collapse, which is basically this collapse that I presented you before, this one, has these spheres, here the part outside is Schwarzschild, etc. This is a well-known thing from 1939. Now, we know that this Oppenheimer-Snyder collapse has this picture and forms trapped surfaces. Therefore, if you take initial conditions which are close enough to Oppenheimer-Snyder, but without assuming spherical symmetry or dust or anything else, you will still have your trapped surface due to this mathematical problem of hyperbolicity. This happens for the collapse, and this also happens for anything which is close to Robertson-Walker models, because you have proven that in Robertson-Walker models you have trapped spheres. Now, if your universe is close enough to a Robertson-Walker one, not exactly the same, but close enough, then you will have the singularity in the past. And this is the key point that I would like to emphasize. This is the very key point in the singularity, in the Penrose singularity theory, because it proves that these singularities are going to occur independent of whether you are using, trivial models like Robertson-Walker or spherical symmetric dust. Now let me go to some classical singularity theorems after Penrose. Now this Penrose's paper was published in 1965. Then there have been many theorems since then, but you don't have to worry too much because all of them have the very same skeleton, the same pattern. They all look like this. So you have to assume you have a space-time, and you have to assume a condition on the curvature. This is usually the convergence condition. You have to assume a causality condition. In the Penrose theorem, it was the Cauchy hypersurface. And then you need an appropriate initial or boundary condition. In Penrose theorem, this was the trapped sphere. And you always need these three things. And then always the conclusion is that your space-time has incomplete geodesics. Now, for example, the simplest singularity theorem, proven by Hawking 1 year after Penrose, is this one. You take the existence of a Cauchy hypersurface, you assume that the trace of its second fundamental form is positive and is larger than any positive value. This is what this is telling you, is that this Cauchy hypersurface is expanding. So, for example, if you think that your universe is expanding everywhere, this will be satisfied. And then you assume the convergence condition as usual. In this case, you only have to assume the convergence condition along the geodesic congruence, which is orthogonal to the Cauchy hypersurface. Then you can prove that all time-line geodesics are incomplete to the past. This is what you would call a Big Bang. Very simple and very applicable. Now, the paradigmatic case of the singularity theorem is the celebrated Hawking-Penrose in 1970. It's considered the singularity theorem par excellence. And this looks like this. You assume the convergence and causality condition. You also need something called generic condition. Don't have to worry about it too much now. And then they give you three possibilities for the boundary condition, which is either you have a trapped surface, or you have a closed achronal set without edge, which is essentially this is telling you that you have an instant of time which is compact, or you can also have a point with whose light column starts to reconverge. And then in all cases, the spacetime will be incomplete. Now, let me give you some ideas behind the proofs, and then I will use this to discuss my examples. What about the curvature condition? Well, this is usually referred in the textbooks as the energy condition, also the generic condition. But as I explained before, this is an assumption of geometric nature. So you can use it in any of your theories. Only thing you will have to justify whether this is a good condition in your theory or not. Now, this is absolutely indispensable. You cannot prove a singularity theorem without this. This enforces the focusing of geodesics via the Ricciarduri equation that I showed you at the beginning. Now, the second thing you need is the causality condition. In the Hawking-Perron's theorem is the non-existence of closed time-like curves. But basically, the idea in the end, if you follow the proofs, is that you will do everything in a globally hyperbolic spacetime. This means that there is a Cauchy hypersurface. And if you have a Cauchy hypersurface, then this ensures the existence of maximal geodesics between any 2 points. Of course, causally related points. But maximal geodesics cannot have focal points. And this is the thing, you see. You are assuming your curvature condition, which tells you and enforces that all the geodesics are going to focus and produce focal points or caustics. But then you are also assuming, on the other hand, that there must be maximal geodesics between any 2 points, and they cannot have focal points. So, in a way, this is what I have just said. A contradiction somehow starts to glimmer if all the geodesics are complete, and this is where you somehow prove that they cannot be complete. But this is not true so far. There is no such contradiction yet. And I will show you an example, a very nice example of this. And this is because we have not enforced an upper bound, a finite upper bound, for the proper time of the geodesics that are going to be. But to get the contradiction is where you need the boundary condition. This is where you need either your point with the converging light cones or the trapped sphere, etc. Now, later I will discuss some examples. Now, let me go. I mean, this is like the nice part, saying these are the nice things about the singularity theorem. But now, let me go to some remarks that I would like to make. Because singularity theorems are, full of, surrounded by a lot of myths and folklore that I would like to explain. So, for example, sometimes the Penrose theorem is interpreted as proof that black holes form in gravitational collapse. Actually, the Nobel Committee said something like this, but not quite. But the actual fact is more subtle than that. It's not like that at all. I mean, the gravitational collapse is given by, Chandrasekhar limit, Oppenheimer's light, Snyder, Oppenheimer, Volkov, etc., and then they work by the Russians. In the Penrose theorem, the assumption of the existence of the troposphere, it cannot tell you anything about the formation of black holes. Not at all, because this is telling you something when the black hole has already formed. And I will explain this why. So the Penrose theorem, what it's telling us is something that happens inside the black hole, so beyond the horizon, once they have formed. And this is not bad, this is a good thing, because we cannot know anything from inside the black hole by doing observations. But it seems that by doing mathematics, we can learn things, like, for example, the existence of trapped spheres and singularities. So let me go back to this picture here. So this is the conformal diagram or Penrose diagram of the collapse. If you live outside the black hole, which is this area beyond the horizon there, means that you will go to infinity. So whether you will go to I plus or this thing, which is called phi plus. You see, you will never see the black hole. You will see the surface of the star, but you will never see the black hole. Not only that, you will never be influenced by the black hole. You will not even feel the gravitational field of the black hole, because the gravitational field of the black hole propagates, causally. And therefore, the gravitational field that you are feeling here is the gravitational field of the star that produces the black hole before it becomes a black hole. And this is what happens whenever you are outside the black hole. Of course, you can let yourself fall into the black hole, and then you will feel things which are inside the horizon. But there is a very key point here, is that there is a theorem that this trapped surfaces cannot go outside the event horizon. They will never be outside the event horizon. So you cannot even see them either unless you enter into the black hole. So this is a theorem by Hawking and Claudel that tells you that if you are in an asymptotically flat space-time, no closed trapped surface can be seen from infinity. In other words, they are enclosed beyond the horizon. And therefore, Penrose's theorem is telling us something that happens beyond the horizon, not in the formation of the black hole, but once it has formed. So it tells us something about the interior of black holes. It's telling us that if you have black holes that have formed inside them, they will be probably closed surfaces, and therefore the space-time, in a classical sense, will become incomplete. From the viewpoint of the formation of black hole, you have to do something else. This was done in the 60s and before. And now the important thing is to know whether if you have initial conditions which are innocuous, whether the trapped surfaces will form. And there are nice mathematical papers by Christodoulou and these guys doing that. Now, a little bit more about the small print in the theorems. Now, in 1989, I found this solution. This is a very, very simple metric. It's given in cylindrical coordinates. It has cylindrical symmetry. So partial z and phi are Killing vectors. Sorry?
May I ask you one question?
Yes, yes, yes.
If you go one slide back.
Yes.
So in this context, maybe can I, so I can, one more slide where you had the Penrose's diagram. So, so once I'm crossing the Schwarzschild horizon, I can always see essentially the trapped surface. That's what it means. So in this context, can I imagine that my inside the horizon is a kind something like FRW background?
Inside the horizon, there is expansion, but this is not like a Robertson Walker. It's rather like one of these Bianchi models because it's anisotropic. Now, an important point is that actually, even if you enter into the horizon, I mean into the black hole, you will not be able to see the trapped surface in its entirety. Mm-hmm. This is a paper, famous paper by Wald and Eger, I think, where they prove that even if you enter in a Schwarzschild, you will never be able to see the entire sphere because of how the light propagates towards you. But anyway, you will cross them. I mean, they will be there sometime.
Right. So in finite time, you will definitely cross them.
Oh, yes, yes. I mean, every point here in this region in gray represents a trapped surface in this model because this is the Schwarzschild outside. Yeah. So you are crossing them all the time. Yeah. Okay. Shall I go on? Or? Yeah. So I was telling you about this particular solution that I found. So you can see that it depends only on T and rho. And now the nice thing about this solution is that this is a solution of the field equations with no cosmological constant, but for this equation of state. So it's P equals 1/3 of rho. So this is realistic for radiation-dominated areas or matter. And now this is the density, and of course the pressure only have to divide by 3. And you can check that this is regular everywhere, that the density does not blow up or anything like that. It goes like the hyperbolic cosine to the -4, T and rho. Now this solution happens to be geodesically complete, and it's globally hyperbolic, meaning that if you take any T equals constant hypersurface, these are Cauchy hypersurfaces. Now, if you compute the trace of the second fundamental form, this is the trace. So this is the expansion, so to say. You can see it depends on T. For negative T, this will be negative. At T equals 0, it vanishes. And for positive T, it expands. So this is like the zeta. I mean, this is something which is, it's a perfect fluid which is contracting. Then something halts the contraction, and then it starts expanding. So for any value of T greater than 0, you have Cauchy hypersurfaces. Of course, all the energy conditions are these curvature conditions are satisfied because this is a very nice equation of a state, and the density is positive everywhere. And Joule expansion is for T greater than 0 is positive everywhere. So how can this fit with the Hawking theorem, for example, or with other theorems? So actually, this was thought to be impossible at the time, and then this had some this created some confusion. And the thing is that, as I said, this space-time satisfies all the convergence conditions, all the curvature conditions, so the fusion effect takes place. And of course, being geodesically complete, that you can prove it is, there are maximal time-lapse geodesics between any 2 points. And these maximal time-lapse geodesics will not have focal points. But whenever you have any geodesics, eventually they will have focal points. How can this happen? And the idea is that this happens because the expansion is not bounded below by a positive constant. In the Hawking theorem, K was not only assumed to be positive, it was assumed to be greater than a strictly positive constant. So this is expanding everywhere, but when you go to infinity in rho, the expansion decreases, and eventually at the limit it will go to 0. So it is expanding everywhere, but with no limit. And this little difference makes the possibility, allows for the possibility that this model is geodesically complete. And it avoids the Hawking's theorem, and it avoids all the other theorems. You can prove that there are not flat surfaces, of course, because it is geodesically complete. So the boundary condition is not satisfied in this model. So be careful. It's not enough to say, if my universe is expanding everywhere and my energy conditions are okay, or I have a perfect fluid with the equation of a state, then I will have singularities. That's not true. Now, there is a problem about the extensions that I would like to remark. Because what the...
Jose, if I may ask again. So
yes.
there was also this, so in your example, at some point in past, you hit the de Sitter kind of phase or something like that you mentioned?
No, it's just that I mean, when you go to infinity, this goes like flat because there is no cosmological constant.
Okay.
Either to the future or to the past, if you go to t plus or minus infinity, this is like flat. But of course, there is matter there, and this matter starts collapsing. The thing is that there is the matter. So this is these are co-moving coordinates. You can compute for the velocity vector, which is dt with this factor. You can compute the acceleration, and the acceleration is non-zero. So the fluid is not geodesic. But acceleration comes from a gradient of pressure, and the gradients of pressure oppose the gravitational attraction, and this is how this can happen.
I see. Okay. Thanks.
So I wanted to say something about extension. The thing is that the theorems prove that geodesics are incomplete. Okay, but this may be not the problem, may not be a problem of the spacetime itself. Maybe to cut some part of the spacetime, by hand or whatever. And this is why usually the study of singularities is restricted to manifolds which are inextensible. However, the problem from the physical point of view is hidden under the carpet doing that, because this is not the solution. Because what are we supposed to do with a spacetime which is extensible? Well, the answer may seem simple. Well, just extend it, and then if it is also extensible, extend it again until you cannot extend it anymore. But this is not so simple. And the reason are, physically meaningful extensions are far from obvious. Extensions are not unique. You may think that, you start with a Schwarzschild for air R greater than the gravitational radius, and then you extend like Kruskal. No. I mean, this is one extension, and it's analytical, but there are many, 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 many others. There are infinite in equivalent choices there. And even analytical ones sometimes are not possible, and in other cases, they are not advisable. And even more important, you may choose some extension which are equivalent to other ones, that they may lead to near extensible spacetime, or to singular, meaning incomplete spacetime, or to singularity free. And then which one are you going to choose? Well, you may think, okay, I will choose the singularity free because it's nicer. But this is not what you do usually, because the singularity free one may violate some of the physical conditions that you want to enforce. So how to choose the extension? Now, I want to show you an example, and I hope this picture can be understood. Now, this is the Kerr black hole maximally extended. Now, I have to produce two Penrose diagrams because the picture is different at the equatorial plane than at any other value of theta, theta being the latitude. Now, the picture on the left is the equatorial plane, and then you have the singularity at r equals 0, which in this case is time life, by the way. And any other value of theta, there are no singularities. Now, the original Kerr metric is just, as usual in these cases, is just this part outside, this region 1. And of course, there is this gray region, which is I think it's supposed to describe the ergosphere, and then there is the horizon. Now, if you do the traditional extension, then you will go to the region with trap surfaces, which is this region here. And if you do something like Kruskal, then maybe you get another asymptotically flat region, etc. Now, if you take a Cauchy hypersurface here, you see this is infinity, right? So if you take a Cauchy hypersurface, is something which goes from there to there. Now, this Cauchy hypersurface is not a Cauchy hypersurface for your extension. It only predicts this region. And this is why this is called the Cauchy horizon. Now, the Penrose singularity theorem predicts that your spacetime based on this Cauchy hypersurface, which is non-compact, is going to be incomplete. But what it predicts is the incompleteness here at the Cauchy horizon, not anything beyond that. But of course, the metric is extensible. So now what do I do? And now there are several ideas in the literature. One is that the Cauchy horizon is unstable, and this will become, in any realistic world, the singularity. The other one is, no, you have to extend, and then you can choose the analytical extension or others. Now, if you choose this extension, which is the traditional one in textbook, then of course you get the singularity here. But this singularity is not predicted by the Penrose theorem, and let me tell you, this is not predicted by any singularity term that we know of today. This singularity is not predicted by the theorems. Even worse, if you do this extension, in these regions with R negative, there are closed time-like curves. So if you assume that this extension is nice, then you have closed time-like curves. Of course, then you are not going to be able to prove any singularity theorem with that, because this violates the basic causality condition. So what do I do with these extensions? Do I extend or do I not extend? If I do I extend like this, or do I choose other extensions? Now, this is a problem with the singularity theorem, which is not usually remarked. And now let me finally go to some, whether this is just mathematics and ideas about black holes, or whether they have some observational consequences. And of course, they do have observational consequences. And let me talk a little bit about cosmic censorship, another idea by Penrose. Now, the main question I want to pose now is, can we see singularities? Well, so far, in the spherical collapse that I have presented, the singularity is concealed inside the event horizon of the black hole, and therefore is not visible to external observers, as we have already seen in the layers. Now, but even if you let yourself fall into the black hole, you will not see the singularity in this Oppenheimer-Snyder model, because the singularity is at the future. You know, the singularity is tomorrow. It's at an instant of time in the future. So you will, even if you fall into the black hole, you will see the star all the time until you suddenly disappear in the singularity. Now, these two things lead to these two versions of the cosmic censorship, without this question. Are the singularities produced in collapse of stars or other gravitational collapses even inside black hole horizons, event horizons? This is called the weak cosmic censorship. And there is the strong cosmic censorship, which is actually, are such singularities always non-time-like? So they are either null, like in the Cauchy horizon of Kerr, if this is singular, or irreversible, which is the instant of time in the future. Now, let me show you the picture again. You see, even if you fall into the black hole, so this line is like you are falling into the black hole, you will be able to see the star. You will cross the horizon. You will still see the star all the time. You will see the star. You will see the star, and then you will disappear without ever seeing the star collapsed. It just disappear in the future at the singularity. Now, this is there is a crucial difference with the naive picture. This is the naive picture, and this is what is called a naked singularity. In the naive picture, you keep your light constant 45 degrees, r equals constant are vertical lines, and then the star collapses. And it collapses to the center, and on the center there is a singularity. And of course, any guy here outside can see the singularity. There is nothing preventing that this person sees the singularity. And also, you don't have to follow into the singularity because you can avoid falling. It's not tomorrow, it's somewhere in the space. Now, this is supposed to be completely wrong in gravitation, and this is supposed to be the right picture. And this is called the cosmic censor because all singularities are censored by a cosmic censor says that you will never be able to see them. Now, assuming that GR is, or any other gravitational classical theory, is an approximation that ignores quantum effects in the gravitational field, then of course we will need quantum gravity to understand the true nature of singularities. Now, cosmic censorship can thus be seen as the question of whether effects of quantum gravity in black holes are visible or not, or in the process of gravitational collapse, or even in a more subtle way. Do astrophysicists need to know quantum gravity? Because if they are never going to be able to see or to observe anything close to the singularity, why do they need this quantum gravity? Of course, cosmologists probably do in the Big Bang. Now, cosmic censorship is probably one of the important open problems in general relativity and in general in gravitation. And this actually leads, if I have time, yeah, I think so, I have some minutes, to all kinds of inequalities that involve physical characteristics of the system, like the mass, angular momentum, charge, areas, etc. Let me show you some of them. So assume that you have a closed subsurface. Then there is a famous inequality called the Penrose inequality. That is telling you that the area has to be less than this, essentially the radius square, the gravitational radius square. Now, this has been proven in several situations, but not in general. And it depends crucially on whether cosmic censorship is true or not. This was reduced by using cosmic censorship. Now, there are also these inequalities involving the angular momentum. This J is angular momentum, and the mass. And also there is this general idea by Sergio Dain that the area of the surface has to be always less than this combination of the angular momentum. Now, what happens if I bring lambda into this picture, cosmological constant? Well, if I keep axial symmetry for my object or my surface, then there are these inequalities. They are all based on cosmic censorship. The area of the surface can never be larger than this quantity here. So you may compute how much is 4 pi over lambda to see what is the area of these things. This is the general, this is assumed to be the general inequality between spin and area and lambda if you assume axial symmetry. And also you can extract a maximum which is universal from this thing by just using the Newman black holes and the thin ones and the relation between the area and the lambda. And then you get a universal limit for the angular momentum of closed up surfaces, which is given by this thing here using lambda, this number. We don't know where this number comes from, apart from cosmic censorship. By the way, some of these can be improved, and some of them are claimed to hold for any object, not only for black holes. And now I also want to remark that these inequalities may have consequences concerning the entropy, because the area of black holes is related to the entropy enclosed in them. Now there is this folklore thing about the solution. What is the solution? Well, quantum gravity or quantum effects will be the solution. Well, I think this is what most theoretical physicists do believe, because there is some tension between the singularity theorems and quantum gravity. But on what grounds? Why do they believe that? Now, you see, the theorems tell us that in reasonable situations, the space-time has a margin, something where it stops to exist classically. The space-time is incomplete. However, if you violate the curvature conditions, like the convergence conditions, things like that, for example, by invoking quantum effects, you may ask yourself whether this will help you. And the thing is that in general, or in many occasions, this do not help to avoid incompleteness. So the thing is that, will some kind of singularity theorems survive in quantum theory or gravity? Well, if you want the general discussion, you can read this paper by Boyerwald. And the main line of research in this direction consists in relaxing the convergence conditions, because, you know, we know that a quantum theory will violate, even maybe for a little time or whatever, but due to the uncertainty principle, it will violate the energy condition. Now, results in this direction deal with average energy conditions, and there were original ones were by Tipler, but then there are later ones by Roman. But then you have much better results in analysis in this century, presented by reconsidering the null convergence condition in quantum field theory. And actually, these people, I don't know if is aware of, some singularity theorems have been proven having these effects taking these effects into account. So even assuming that there is violation of the convergence condition by quantum effects. Actually, this has led to a version of the Penrose singularity theorem which allows even for global violations of the convergence condition. Of course, this deals with quantum field theory in curved space-time. So you may think that these are semi-classical regimes, etc. So these are not really quantum gravity. Of course, one should take into consideration the quantum fluctuations of the space-time itself. So truly quantum gravity. Now, the important thing here is that classically one relies on this point-wise focusing of the cause and the reciprocal. But there is nothing like point-like or point-wise in quantum regime. You see, there are not going to be points there. So this cannot be true in the quantum regime. However, the boundary condition can be adapted to possible quantum situations. And there is a nice result in this paper where the notion of a closed trapped surface can be adapted to quantum cases and even used to prove the singularity theorem under this weaker sigma. So far, we don't have any definite proof or evidence that the quantum effects will rescue from the idea of incompleteness of the space-time. Now, just the summary, so I'm finishing. So another thing I want to dispel is that the idea that singularities are essential or they happen in general relativity as a universal thing. This is not true. I mean, all the gravitational systems, so say the solar system or the galaxies or the clusters, whatever, they are all very well described by GR or by its limits using post-Newtonian limits. So there is nothing like singularities in a universal way. They only arise in two exceptional circumstances, which are black holes if they form in collapse and the initial, the origin of the universe. Of course, the incompleteness in the sense of singularities in these two exceptions, this certainly is a distinctive feature of general relativity. And this is the important thing, because the singularity theorems provide supporting evidence for the need of something else. So the theory is predicting its own failure. In a way, it's saying, I am a theory so nice that I'm telling you that I need correction, maybe quantum or whatever. But I need corrections only well inside black holes, not at the horizon in Sagittarius stars, well inside, or at the origin of the universe. Now, I already referred to the problem of extensions. There are also the problems of the type of the singularity. The most powerful theorems like the Hawking-Penrose is not of much application, because if you believe that there is already a singularity at the Big Bang, then this is already predicted, and then it's not predicting anything else, because the Hawking-Penrose theorem is not telling you where or when the singularity is going to happen. And as I said before, there is no theorem that can predict the singularity in the extended Kerr black hole, and probably there will never be. And with that, I will thank you for your attention. I finish here.
So thank you very much. It's a very nice and very thought-provoking talk, and I think many of our colleagues have enjoyed it. So please, from the audience, do you have any question for Jose? Please ask now. Unmute yourself and just ask.
Yes, thank you very much for the talk. Do you have any thoughts on like these recent developments on black hole information, or is there any kind of interaction between the two? Well, is there an interaction between singularity theorems and black hole information paradox?
Well,
ideas?
Not directly, in the sense that singularity theorems just prove, the incompleteness, but yes, in an indirect way, because if you believe that this is going to be something like the event horizon and things like that, then this is where all these problems come about. And of course, yes, there is an interaction. By the way, this last paper I mentioned by Wall deals with that. So this is like using the generalized second law of thermodynamics, and then trying to see how this can be formulated in a quantum manner, and then to see whether the singularities are still there. I mean, not the singularities, but the theorems, whether the theorems work. And yes, there is a lot of work on that. I mean, I don't know exactly what but there is some relation, not direct, but indirect.
Mm-hmm, mm-hmm. But I was referring particularly to this island rule by Maldacena and colleagues that came out like 2 years ago, because they also have like these quantum extremal surfaces, but that's a completely unrelated star. Is that fair to say?
This I don't know, I cannot say.
Okay, thank you.